Electric motors have a limited capacity to withstand high temperatures generated during starting and stopping. Rapid starts and stops can cause mechanical stress on the motor and its components, such as bearings and windings. Each start draws high inrush current, which can stress the electrical system and components. The acceptable starting frequency for a motor depends on various factors. Different motor types have different starting characteristics and tolerances. The load's inertia and starting torque requirements affect the stress on the motor. The electrical system must be able to handle the inrush currents during starting. For a 480 volts motor with a high inertia load, the following guidelines are recommended. The maximum starting frequency is 6 starts per minute. The minimum time between starts is 15 minutes to allow the motor to cool down. Ensure the motor is properly protected by an overload relay that will trip before the motor overheats. Jogging a motor is not an acceptable solution to operational problems. It puts excessive stress on the motor and reduces its lifespan. Train operators on proper motor operation and the consequences of excessive starting. Investigate the root cause of the excessive raw product on the conveyor and implement solutions to prevent it. Repeated starts above the acceptable frequency can lead to overheating. The motor can overheat and fail prematurely. The motor's lifespan can be significantly shortened. Rapid starts and stops can damage bearings. Excessive starting can weaken the windings. Overheated motors can pose fire and electrical hazards. Therefore, understanding motor starting considerations is crucial for maintaining the longevity and safe operation of industrial equipment. The primary considerations revolve around thermal capacity, mechanical stress, and electrical stress, all of which are impacted by the frequency of motor starts. Regarding thermal capacity, electric motors possess a finite ability to manage the high temperatures produced during the start and stop cycles. Each start generates heat within the motor windings due to the inrush current and the work done to overcome inertia. If starts are too frequent, the motor does not have sufficient time to dissipate this heat, leading to a gradual increase in temperature. Elevated temperatures degrade the insulation of the motor windings, which can eventually lead to short circuits and motor failure. Concerning mechanical stress, rapid starts and stops exert significant force on the motor and its constituent parts, including bearings and windings. The sudden acceleration and deceleration cause stress on the bearings, potentially leading to premature wear and failure. Similarly, the windings experience mechanical stress due to the electromagnetic forces generated during starting, which can loosen the winding insulation and compromise their structural integrity. As for electrical stress, each motor start involves a surge of inrush current that can place a strain on the electrical system and its components. This inrush current is significantly higher than the motor's normal operating current, and repeated starts can cause voltage dips and fluctuations in the power supply. These voltage variations can affect the performance of other equipment connected to the same electrical system and potentially damage sensitive electronic devices. Determining the acceptable starting frequency for a motor involves evaluating several factors, including the motor type, load characteristics, and power system capacity. Different motor types have varying starting characteristics and tolerances. For instance, some motors are designed with features that allow them to handle more frequent starts than others. The load's inertia and starting torque requirements influence the stress on the motor. High inertia loads demand more energy to accelerate, leading to higher inrush currents and increased heat generation. The power system capacity must be adequate to handle the inrush currents during starting without experiencing excessive voltage drops. For a 480 volts motor with a high inertial load, it's generally recommended to adhere to specific guidelines to prevent premature wear and failure. A commonly recommended maximum starting frequency is approximately 6 starts per minute. Additionally, it's advisable to maintain a minimum time of 15 minutes between starts to allow the motor to adequately cool down. These guidelines help to minimize the thermal and mechanical stress on the motor and prolong its lifespan. Beyond these recommendations, there are additional considerations to keep in mind. Proper overload protection is essential to safeguard the motor from overheating. An overload relay should be installed to trip and disconnect the motor from the power supply before it reaches a critical temperature. Furthermore, jogging a motor to address operational issues is not a sustainable or advisable practice. Jogging subjects the motor to excessive stress and can significantly reduce its lifespan. Comprehensive operator training is crucial to ensure that personnel understand proper motor operation and the potential consequences of excessive starting. Operators should be educated on the recommended starting frequency and the importance of allowing the motor to cool down between starts. Moreover, it's important to identify and address the root cause of any operational problems that lead to frequent motor starts. Process improvements should be implemented to prevent the need for excessive starting and jogging. The consequences of excessive starting can be significant. Repeated starts above the acceptable frequency can lead to overheating, premature motor failure, reduced lifespan, bearing damage, and winding damage. Overheated motors can also create safety hazards, including the risk of fire and electrical shock. Therefore, it's imperative to adhere to the recommended starting frequency guidelines and implement measures to prevent excessive starting. Understanding the thermal limits of the motor is crucial. Every motor has a thermal limit, which, if exceeded, can lead to insulation breakdown and eventual failure. Frequent starts generate heat within the motor windings. The amount of heat generated depends on factors like the motor's design, the load inertia, and the duration of the start. If the motor doesn't have enough time to dissipate this heat between starts, its temperature rises. The insulation materials used in motor windings are designed to withstand certain temperatures. Exceeding these temperature limits can cause the insulation to degrade, leading to short circuits between windings. These short circuits can result in motor failure and potentially pose a safety hazard. Consider mechanical wear and tear. Each start subjects the motor's mechanical components to stress and wear. The bearings, for example, experience increased loads and friction during the acceleration phase. Frequent starts can accelerate the wear of these bearings, leading to premature failure. Similarly, the motor windings experience mechanical stress due to the electromagnetic forces generated during starting. These forces can cause the windings to vibrate and move, potentially loosening their insulation and compromising their structural integrity. The inrush current can cause voltage drops. Starting a motor typically draws a high inrush current, which can cause voltage drops in the electrical system. These voltage drops can affect the performance of other equipment connected to the same circuit and may even trip protective devices. The severity of the voltage drop depends on the size of the motor, the capacity of the electrical system, and the impedance of the wiring. In situations where the electrical system is already heavily loaded, frequent motor starts can exacerbate voltage drops and create instability. To mitigate these risks, it's essential to follow recommended starting frequency guidelines. These guidelines are typically provided by the motor manufacturer and take into account the motor's design, load characteristics, and operating environment. Adhering to these guidelines helps to ensure that the motor operates within its thermal and mechanical limits and that the electrical system can handle the inrush currents without experiencing excessive voltage drops. Proper motor protection is also crucial. Overload relays are designed to protect motors from overheating by monitoring their current draw. If the motor draws excessive current for an extended period, the overload relay will trip, disconnecting the motor from the power supply. This prevents the motor from overheating and potentially failing. In addition to overload relays, other protective devices, such as fuses and circuit breakers, can also help to protect motors from damage. These devices are designed to interrupt the flow of current in the event of a fault, such as a short circuit or ground fault. Another consideration is the load characteristics. The type of load that the motor is driving can also affect its starting frequency. High inertia loads, such as those found in conveyor systems, require more energy to accelerate than low inertia loads. This means that motors driving high inertia loads will generate more heat during starting and may need longer cooling periods between starts. To further address the situation of an operator repeatedly jogging a motor to correct an issue with material flow, several steps need to be taken. Firstly, it's crucial to implement proper training for the operators. They need to understand the consequences of excessive jogging and the potential damage it can cause to the motor. Secondly, investigate the underlying cause of the material flow problem. There might be a bottleneck in the system, a misconfigured sensor, or some other issue that's causing the material to accumulate on the conveyor. Addressing this root cause will eliminate the need for the operator to manually intervene with jogging. Thirdly, consider implementing automation solutions to control the material flow. This could involve using sensors and programmable logic controllers, PLCs, to automatically adjust the speed of the conveyor or other equipment to maintain a consistent material flow. This will not only eliminate the need for manual intervention, but also improve the overall efficiency of the system. Furthermore, consider installing a soft starter or variable frequency drive, VFD, on the motor. Soft starters reduce the inrush current during starting, which reduces the stress on the motor and the electrical system. VFD allow you to control the motor speed, which can be useful for fine-tuning the material flow and preventing accumulation. Finally, monitor the motor's performance and temperature. This can be done using sensors and data logging equipment. This will allow you to identify any potential problems early on and take corrective action before they lead to motor failure. By taking these steps, you can significantly reduce the risk of motor failure and improve the overall reliability of your industrial equipment. This ensures the overload protection is correctly sized and functioning properly. Overload protection is designed to protect the motor from thermal overload, which can occur when the motor is subjected to excessive current for an extended period. The overload protection device, typically an overload relay, is sized based on the motor's full load amps and trip characteristics. It's crucial to ensure that the overload protection device is properly sized and that its trip characteristics are appropriate for the motor's application. If the overload protection is not properly sized, it may not protect the motor from thermal overload, or it may trip unnecessarily, causing nuisance shutdowns. Verify adequate ventilation and cooling. Motors generate heat during operation, and it's essential to ensure that they have adequate ventilation and cooling to dissipate this heat. The motor should be installed in a location that allows for free airflow around the motor. Any obstructions that could restrict airflow should be removed. Additionally, the motor should be kept clean and free of dirt and debris, which can insulate the motor and prevent heat dissipation. If the motor is located in a hot or humid environment, it may be necessary to provide additional cooling, such as forced air cooling or liquid cooling. Conduct regular maintenance and inspections. Regular maintenance and inspections can help to identify potential problems early on and prevent motor failures. The maintenance schedule should include tasks such as lubricating bearings, checking wiring connections, and inspecting the motor for signs of damage. The frequency of maintenance and inspections will depend on the motor's application and operating environment. In addition to regular maintenance, it's also important to conduct periodic inspections of the motor's electrical system, including the wiring, connections, and protective devices. These inspections can help to identify potential hazards, such as loose connections or damaged wiring, which could lead to motor failure or electrical shock. Review the motor's duty cycle. The motor's duty cycle, which is the amount of time that the motor is running versus the amount of time that it is stopped, can also affect its starting frequency. Motors that are subjected to frequent starts and stops will generate more heat than motors that run continuously. If the motor's duty cycle is particularly demanding, it may be necessary to derate the motor or provide additional cooling. Consider using a motor with a higher service factor. The service factor is a multiplier that indicates the motor's ability to handle occasional overloads or high ambient temperatures. A motor with a higher service factor will be able to withstand more frequent starts and stops without overheating. However, it's important to note that using a motor with a higher service factor will not necessarily solve the problem of excessive starting. It's still important to follow the recommended starting frequency guidelines and implement measures to prevent excessive starting. Consider implementing a soft starter or variable frequency drive, VFD. Soft starters and VFD can reduce the stress in the motor during starting. Soft starters gradually increase the voltage applied to the motor during starting, which reduces the inrush current and the mechanical stress in the motor. VFD allow you to control the motor's speed, which can be useful for applications where the motor needs to be started and stopped frequently. Additionally, VFD can improve energy efficiency by allowing the motor to run at the optimal speed for the application.